Um, Welcome everybody to the Asia Pacific Analysis and PDE seminar. Today it's a great pleasure for me to introduce Professor Yihong from the University of New England. Yihong obtained his PhD in 1988 from Shandong University in China after spending 2 years at Shandong as a lecturer and 1 year at Heriot-Watt University in the UK as a visiting fellow. He joined the University of New England in 1991 as a postdoctoral research fellow, working with Professor Dancer, who is now at the University of Sydney, but formerly he was a professor at the UNE. And Professor Yihong was promoted to professor in 2008 at UNE. While being affiliated with UNE, he visited Heriot-Watt University under the Australian Academy of Science and the Royal Society Exchange Fellowship, visited the Chinese Academy of Science under 2 Australian Academy of Science Exchange Fellowships, visited the University of Tokyo and Waseda University under the Australian Academy of Science and GSP Fellowship. And he visited several other institutes in the world, among also Minnesota, the National Center of Theoretical Science of Taiwan, and was a visiting professor there, and also an adjunction professor at Khufu Normal University in China for 6 years, from 2004 to 2010. I had the honor to get to know Yihong in 2013, where he invited me the first time at Armidale in Australia, and there I had the occasion also to meet Professor Matano, where they both worked on Fisher-KPP models, still the local version. Today, Yihong will speak about spreading rate for the Fisher-KPP non-local diffusion equation with free boundary. So it's a great pleasure to see your new results in this direction. Yihong, please start.
Well, thanks, Daniel, for the introduction. And it's nice to be able to talk about some recent results at this Asian Pacific seminar. And I so many friends are here. However, I couldn't see them. And thanks for coming. So that's a rough plan of what I want to do today. I'll cover some background and then move to the main part of the talk, and this on the non-local diffusion equation with the free boundary. And here I explain the 1D, one space dimension case, and also report some new results on high dimensions with reduced symmetry. And if there's extra time, I also want to mention very briefly some extensions in other directions, basically concerns systems of equations in one space dimension. So now let me start by looking back to the classical Fisher-KPP equation. And that, so as many of us know, KPP stands for Kolmogorov, Petrovsky, and Piskunov. So in 1937, in 2 independent papers and in these pioneering works, so this semi-linear parabolic equation was first used to describe the spreading of a population. And here, so this U as a function of time and space for space variable in these classical works, concentrate on the one space dimension case. So this U represents the density of the concerned species at time t and space location x. And here, this is the initial population, and naturally we assume it's non-negative. And also because we are interested in the spreading behavior, so we consider the situation that initially the population is locally concentrated. In other words, so this non-negative function has non-empty but a compact support. And this function, this is the nonlinear term here in the equation, and it's usually called the growth term. And usually we assume it's a C1 function, at 0 is 0. So when there's no population, there's no growth. So that's natural. And this term is called the reaction, the diffusion term. So that is used to describe that the dispersal of the population is through the so-called local random walk. So I'll explain this in a moment when I want to explain what is non-local diffusion. So for the moment, let's just use this local random walk to describe this. Now for the growth function, a very commonly used class among several is these Fisher-KPP type nonlinear functions. So very simple. It's just a degree 2 polynomial, a quadratic function. So the reason so this model becomes so important and well known is because of this feature. So with this nonlinearity, so it's known that if you look at the long-term behavior of the solution, so its behavior changes depending on whether the space variable is inside this interval of length twice C star t or outside of it. So outside of the population is small, converts to 0 uniformly. Inside, it converts to 1. And at around C star times t, there's a transition. And biologically, and this C star is interpreted as the spreading speed. So the population, you are interested in the local population, how does it spread? Well, this model tells you, well, it spread with a finite speed C star. Well, how to determine this C star? And that was actually discovered already in these pioneering works. So to find this C star, actually you look for a family of self-similar solutions, these special kind of solutions. And these special kind of solutions actually satisfy ODE. So these ODE with boundary conditions. And for this one, with this Fisher-KPP nonlinearity, is known from the Fisher-KPP days that, so this C star equals 2 square root D. So this square root D is D is the diffusion rate, determines the spreading speed. And that's when you look for these kind of solutions. Nowadays, we call these traveling wave solutions. And this C here is called the speed, velocity of the traveling wave. So through ODE analysis, you can show for C greater than or equal to this C star, you have a unique solution subject to translation. For C less than C star, you don't have such solutions. So this C star is called the minimal wave speed. And that determines the spreading speed of the original model. Now, of course, this nice simple model one is not perfect. It has some shortcomings. One shortcoming is that it really doesn't tell you what's the population range for a given positive type. Because you look at this set, that's usually what you define the natural population range. But this one, though at t equals 0, this is a finite set, but when t is greater than 0, due to the strong maximum principle, this is R in space dimension 1 all the time. But this, of course, doesn't spoil the application, and we can nominate a small delta to look at this set. For any delta greater than 0, no matter how small it is, this set actually is always a bounded set. And if you use an interval to enclose this set, and if this is the smallest such interval, of course, it depends on this delta. And then you can look at how the boundary changes with the time. And this you can regard the boundary of these as the spreading front of the species. So this is the population range. And then because of this result, and you can show very easily that the right end of the front of this interval goes to infinity like C star times T. The left end like C minus C star times T for large T. So that's why we interpret the C star as the spreading speed. Now, in the paper appeared in 2010 with Zhigui Lin from Yangzhou University of China, we considered a modification of the classical model so that we can get the population range a finite set in space dimension 1, a finite interval all the time. So this is the same semi-linear parabolic equation and similar initial condition. But now we assume, so this is satisfied only on a moving interval, and that is treated as the population range. At the boundary, the population is 0. However, to make the math problem well posed, we need to add one more equation to govern the evolution of this population range, the interval. So this is borrowed from the Stephan condition. And on the surface, it says the range of expansion of the population range is proportional to the gradient of the population density at the boundary. And well, we could also deduce these from certain biological assumptions. It's done in this paper joined with Bontin and Krakowski, my colleague at that time at the University of New England. So now with this modification, of course, we gained something. So now we know the population range is always a finite. It has a clear front, that's just a boundary, determined by what we now call these in mathematical free boundaries. So they are moving boundaries. And the long-term behavior is described by these. So firstly, long-term, we have two possibilities. The population might spread successfully. The population range converts to the entire available space, which is R, and the population density converts to 1. So the carrying capacity in the model. Or the other possibility would be, we call it vanishing. So the population vanishes eventually. The density converts to 0 uniformly, and the population range stops, well, converts to a finite interval. So it basically stops growing gradually. So the difference, spreading successfully and vanishing. And moreover, when spreading happens, we can also show there's a spreading speed. So the range boundary, so GT and HT, they go to infinity like a constant times time. So one goes to positive infinity, one goes to negative infinity. And this constant C0 can also be uniquely determined by looking for traveling wave solutions. And moreover, with this regarding this dichotomy, if we use the parameter mu appearing here as a changing parameter in the model, and we can find a threshold value mu star, so spreading happens exactly when mu is greater than mu star. Now, how to determine this spreading speed C0? It depends with mu. Well, you look for you look for a self-similar solution, a wave-like solution. You reduce the problem to an ODE, but now instead of ODE over the entire R, is on a half space, or half of the R1, half of the x-axis, the real axis. And we have boundary conditions. And because of these free boundary condition, we need one more condition. But nevertheless, so this problem we can show has a unique solution pair. So the speed C is unknown, the profile Q is also unknown, but we have a unique solution. You give me mu, I have a unique solution, unique speed. So that's one difference from the classical case. When you look for a traveling wave solution, you don't have a unique speed. The minimal speed gives you the spreading speed. Now here, so we have a unique speed. So that's one of several very important difference between the model 2 with the free boundary and the classical one, which is equation 1. Now also they are related. One relation is that, so you can view the classical model as a limiting problem of the free boundary model 2 by letting the parameter mu go to infinity. So if you let mu go to infinity, then the solution of the free boundary problem would behave like that. So the population range would go to R when mu goes to infinity for any fixed t. Actually, for any t in a compact set in the open interval 0 infinity. And the solution U would convert to the solution capital U of 1, provided the initial functions of the set. So therefore we can say, so 1 is a limiting problem of 2. And here it enhances this observation. You look at the speed. So the model 2, the speed converts to C star determined by 1 when mu goes to infinity. And so here I mentioned these basic feature of problem 1, the classical Fisher-KPP equation. The version I used here is from the classical paper of Aronson and Weinberg. And those for problem 2 is taken from my joint paper with Zhigui Lin from Yangtze University, joint paper with Zhongming Guo from Henan Normal University, and also joint paper with Bendong Lo from Shanghai Normal University. And for both 1 and 2, I only mentioned the very, very basic cases. And there are now many extensions. So these basic results have been successfully extended in many directions. For example, to high space dimension, to many systems of equations, and also many situations where you assume the environment is not homogeneous, but is heterogeneous. Only certain types of heterogeneous environments, like periodic in time, periodic in space, or you have a shifting environment with a constant speed, this kind of thing. But so today I want to focus on the diffusion assumption. So the dispersal in 1 and 2 are represented by this local diffusion term. And in many situations, these are not ideal. And if you replace it by some so-called non-local diffusion operators, it would be more realistic or explain what local diffusion operator mean here today. Anyway, so the extension of the classical Fisher-KPP equation 1 from the local diffusion case to the non-local diffusion case has appeared from quite a while ago, more than 20 years ago, and there are still many researchers working in this direction. But the extension for the free boundary problem is relatively recent, and that's what I want to talk about today.
Yihong, before you continue, may I maybe briefly ask the question between the main problem 1 and the main problem 2?
Yes.
How did you got motivated basically there? So why is it more natural to look in problem 2 than instead of 1?
Yeah, that's related to this question. So very often we want to know not only the spreading speed of a species, especially when we talk about epidemic diseases. So you care very much about where is the range boundary. So when does this disease reach us? So, but this classical model one doesn't really tell you, because so if this really is used in for, well, it's not suitable, but if this is really used for COVID spreading, then determining delta would be a political issue, right? So to approximate the front.
Yeah.
So this model itself does. So one of the main motivation was to try to modify the model so that we know the boundary of the population range.
Okay.
And then this introduced the free boundary. Yeah.
Thank you.
So now the one class of rather commonly used non-local diffusion operator looks like that. So you replace the local diffusion term by this term. Well, what do you mean by this term biologically, for example? Basically, this means an individual of the species at location X, so would move to a different location Y with the probability given by this. So of course you discretize your model, you discrete time into time moments from the current moment to the next moment. So your species move, and that's the assumption on how it moves from X to another location Y with the probability J. Now, what's the difference from the local diffusion operator here? Well, when discretized, so you discretize your R into equal length, the small intervals, infinitely many of them. And these can be obtained by assuming that an individual at the current local interval would move in the next time moment to either the left neighboring interval or the right neighboring interval with the probability half. So the focus is on the neighboring interval. But here in the non-local diffusion, and it can jump from X to any Y with a certain probability. So this is non-local. And then for the classical Fisher-KPP model, you just replace this term by this blue one, the non-local diffusion term, and you keep your F unchanged, you keep the same initial function, and that would change your assumption on the dispersal of the species. Now, what's the, so in terms of this Fisher-KPP equation, what's the big deal if you change the assumption on the dispersal? Well, for the dispersal kernel, let me mention some usually taken assumptions, not always. So say it's continuous, non-negative, even, and normalized. And then one important classification for the kernels is according to its behavior. Basically, it's tail behavior. So if this integral is finite, you call this J thin tail. So if for some lambda, so you multiply it by a to the lambda x, this is still integrable. So you already have that, but you assume furthermore that. And then if that is satisfied, you call J a thin-tailed kernel. Otherwise, you say it's a fat tail. So for problem one, when you change the diffusion strategy to non-local to obtain 3, and actually you found that for thin-tailed kernels, many of these basic theory for the local diffusion problem one carry over from many works. I just mentioned some names for people who started early, and there are many other people working in this area. But for fat-tailed kernels, now there's a new phenomenon, and it's called accelerated spreading. So it's best illustrated here. So we consider problem 3 with the same Fisher-KPP nonlinearity F, we only change the diffusion strategy from local diffusion to non-local diffusion. And the behavior is similar. So now for any t positive, the solution is positive everywhere. And when t goes to infinity, the solution converts to 1. That's exactly the same as for 1. However, you also want to like to check the spreading speed. And again, you nominate this set omega delta to represent the population range, and you check the rate of its range boundary. How does it go to infinity when time goes to infinity? Well, this quotient now goes to a finite number, say star, when j is thin-tailed. Otherwise, it's infinity. So this basically says the range boundary grows linearly in time. This is a superlinear, so accelerated spread. And if you choose kernel functions whose tail at x near infinity behaves like that, and this is from a result of Bargania, and it says, well, then these functions go to infinity exponentially. If it's behaving like that, still not a thin-tailed because beta is greater than 1, then these functions behave like t to the beta greater than 1. It's superlinear, but faster than linear. And also you can look for fractional Laplacian problems, which arises when you assume the random walk is not a local random walk, but it can jump, the so-called Levy jumps. And then you get a kernel function like this. Well, it's a singular, and it's not integral. That's in dimension n. If you take n equals 1, you come back to 1 dimension. But so this really is not covered by these. But so the behavior of the spreading is similar. So again, you choose the Fisher-KPP nonlinearity. That's from a result about Cabrera and Roque-Jeffrey. And you can show this transition happens at around a to the sigma star times t. So sigma star equals this. N is the dimension, S is the power here in the fractional Laplacian. So this is, again, accelerated spreading. Okay, now let's look at these.
Yihong, there is a question by Professor Van Golders. Is it okay that?
Yep.
Ben, can you speak, please?
Yes, I can, but Professor Du already answered this question in the next slide, so I don't have to ask about it. Thank you.
Okay.
Thank you.
So now, so in one space dimension for the free boundary model, basically we can do the same. Replace the local diffusion term by this same non-local diffusion term. And we still use the same differential equation, but then, so it's over this population range, which is this finite interval all the time. And at the boundary, the population density, we assume is 0. And we have initial conditions, these natural, but this time we have to use these kind of equations to govern the evolution of the range boundary, G and H. So this is derived from the same kind of biological assumption as what we did for the local diffusion case. I might be able to say a few words about it. So this is the assumption on the initial function is continuous, positive in the range, and equals 0 on the boundary, and that's the usual assumption we take for the kernel function: continuous, non-negative, normalized, even, and finite all the time, and so on. So for the nonlinear function fu, again, we take the Fisher-KPP one. And so, so what is this? So this, you can say, is exactly this quantity here. Actually, according to the meaning of this kernel function, this really represents the, we call it the outward outward flux at this right boundary of the population range. So populations, if we consider plants population, so they spread maybe by, they get carried, their seeds get carried by wind or by birds, insects. So those carried away from the population range. So it's difficult to be what's the word? Yeah. So for rebirth for the next generation, pollination is important, for example, and carry far away, they will die. They cannot produce the next generation, but some nearby ones would survive. And so these would enlarge the population range. So we assume the rate of enlargement of the population range is proportional to this quantity, the outward flux. So that's what happens. And this model 4, that was proposed independently in these 2 papers in the same year. And so in this second paper listed here, they consider only the case F is identically 0. So here we consider F, which is Fisher-KPP. But the assumption the assumption for these free boundary condition in these 2 papers are exactly the same. Now, what's the behavior for this non-local model with the free boundary? Well, we can prove existence, uniqueness. We can also have this dichotomy. This is basically identical to the local diffusion model with the free boundary. Now, of course, when we determine the criteria for spreading or vanishing, we found a difference. So this second case is basically identical to the local diffusion case. But this first case is new. In the local diffusion case, you don't have that. So in all these situations, whether D is less than or equal to this or greater than that, in the local diffusion case, you have these. But now, so that's one difference. But of course, the most important difference is again when we look at the spreading speed. So we know, as I said a moment ago, for the classical Fisher-KPP model with the non-local diffusion, and so whether the speed is finite or infinite depends on whether the kernel J satisfies the thin-tailed condition. Corresponding to that, for the free boundary problem, that threshold condition is this one. We call it J1. So this is integrable. So this basic assumption says J is integrable, but now you need X times J to be integrable. So if this is satisfied, we have a similar situation like in the local diffusion case with the free boundary. If this is not satisfied, we have accelerated spreading. So this ratio goes to infinity. So this is taken from a joint work with Fang Li from Guangzhou, and also Maolin Zhou from Nankai University. Maolin actually did his PhD at Tokyo University with Professor Matano, and he joined me at UNE as a postdoc, but he went to China a year ago. Now, how to determine the speed C0? Well, that's again the old trick. You look for wave-like solutions, and this time the problem reduced to not an ODE, but a differential integral equation, but without time. For this problem, we can show if J1 holds, we have a unique pair, C. So C and phi are both unknowns. C is the speed, phi is the profile. But if J1 does not hold, we don't have a solution pair. So this J1, actually, we discovered the condition J1 from here. And then we went back to prove this. So now I want to also talk a little bit about the rate of spreading. So this is a rather rough description. The speed is either, asymptotic speed is either finite or infinite. So can we be more accurate about that? Well, we have to add more assumptions on the kernel function because our initial assumption J is too rough, even J1. So if the kernel function, the tail behaves like x to the minus alpha at infinity, and then with this assumption, so the basic assumption J is equivalent to R alpha greater than 1, J1 is equivalent to alpha greater than 2. And we can show then, so when J1 holds, we can ask, well, what's the difference between the linear function and these free boundary function, the range boundary? Well, if alpha is greater than 3, we can show this is bounded. But if alpha equals 3, it's still in this range, but this is no longer bounded. Equal 3, the gap is of order log t. If it's between 3 and 2, it's this. So this is still, so 3 minus alpha is greater than 1. So this is even higher order than this one. Now, if alpha equals 2, then J1 is no longer satisfied. So we don't have a C0 anymore. Now we're in the case of accelerated spreading. So when alpha is between 2 and 1, including 2, so we are no longer in this case. Of course, alpha has to be greater than 1 because we assume J. Now, how fast does this go to infinity? Well, alpha equals 2 is t times log t, superlinear, but it's like this. If alpha is between 2 and 1, is t to this power. So this power is greater than 1. So these are cases of accelerated spreading. So this is taken from a recent joint work with Wenjie Nei, who is a postdoc working with me now. So if we pause to compare, so compare 3 and 4, and also compare with this local diffusion case 1 and 2. So between 3 and 4, let's recall, accelerated spreading for 3, the one without a free boundary, but with a non-local diffusion, is determined by J has a fat tail. So, and for 4, accelerated spreading happens if J does not satisfy J1. And the J1, J thin are comparable. So J thin implies J1. It's rather clear, but not the other way around. But if we compare with the local diffusion models, whether the classical one or the one with free boundary, whenever spreading happens, you don't have accelerated spreading. So really this accelerated spreading is caused by this non-local diffusion by the kernel having a tail not convert to 0 fast enough. Okay, now let me also quickly mention what happens in high dimension. In high dimension, to avoid complexities, we consider the radial case. Without a radial symmetry, the regularity of the free boundary could be a very technical, difficult problem. So for them, well, that's what we want to look at eventually, but before that, we want to try to have a feeling about the dynamical behavior. So in high dimension with the radial symmetry, the free boundary problem would look like that. The population range would be a ball of radius changing with the ht, and the boundary is 0, and the rate of spreading of the population range is proportional again to the flux. That's initial condition. So this is the natural extension of the one space dimension case to high dimension with the free boundary with non-local diffusion. So here we have the kernel function J, which is the radial. Again, we assume we take these standard Fisher-KPP nonlinearity. And so this part is from another joint paper with JNA. It's just a preprint. And for the kernel function now in higher dimension radial, but we still assume it's continuous, bounded, and non-negative, and at 0 is positive, normalized. And well, because it's radially symmetric, if we write this U in terms this as R, as one variable, we can change 6 into this form. So, and then the kernel function is not the original J, is obtaining this way from J. And this looks like a one dimension case, and the boundary is 0, and that's the free boundary condition using the J tilde, and due to high dimension, we have this term, and that's the initial condition. And we can show we have no problem with the existence uniqueness. We can again prove the same kind of spread and vanishing dichotomy. And these criteria is almost identical to the case of a one space dimension. You look at the detail, it's similar to the one space dimension non-local diffusion model with the free bound. Now, of course, we want to know what's the spreading rate. Well, to look at the spreading rate, we have to look at another function produced by the original kernel function, this Jstar. So this Jstar, we defined that way. This is a, so Ksei is in R. So when the original kernel J satisfies black J, the condition J, the standard assumption J, this Jstar satisfies the standard assumption for the one dimension spatial dimension case, Jstar. And also this Jstar, well, this, if you do a calculation, you can find Jstar is given in this way by the original J. So the dimension appears here. And also Jstar times its variable Ksei equals original J times R to the N over this range. So the integral is the same. It's not the integrand are equal. So the integral are the same. Now to determine the spreading rate, we have to use this Jstar. So if Jstar satisfies J1, we have a finite speed. If Jstar does not satisfy J1, we have infinite speed. Well, so this is Jstar. So J1, let's recall, is this integral is finite. In terms of J, is this integral is finite. And moreover, this C0 determines, so these finite spreading speed. Okay. Yes, this C0. And now, of course, we know how to determine this C0 because we just use Jstar as in our theorem 5 in the one dimension case to determine that. We use traveling wave solutions. Now, how about the rate of spreading in these high dimension cases? So we looked at two situations. One is the case, the high dimension kernel J satisfies J1. So that's the case, we have a compact support. So in this case, And in this earlier work, I didn't mention that as a theorem, but there's a more general result implying in this case, so this difference is no longer bounded. In one-dimension case, so it's bounded if J has compact support. But now in the high-dimension case, if J has compact support, even have J has compact support, so we are sure we are in this case, but this difference is like log T for large T. So that's one big difference. But how about the other case when J1 is not satisfied? Then we looked at a case where this high dimension kernel J behaves like a power function near infinity. And then we know, so J1 does not hold exactly when beta is in this range, n is the dimension. Let's recall when n equals 1, the behavior of these I just mentioned is like this, depending on whether beta is 2 or between 1 and 2. In high dimension, this rate under this assumption is similar. You see, the only difference is now the dimension is n. We replace these by n. And now there are still many questions we want to answer, but we are not able to at the moment. For example, if we look at these power-like kernel functions, and J1 would hold if beta is greater than n plus 1. So this is the case. Accelerated spread in J1 does not hold, but when beta is greater than n plus 1, J1 holds. And we have this by theorem 10. But what's the difference? So we want to figure this out. We are still working on that. And the other is, well, we mentioned, for example, in theorem 11, this is of order LNT. But you can ask, would this over LNT convert to a constant? We believe so, but we are not able to determine that for the moment. And similarly, in theorem 12, you can ask whether these limits exist. We believe they exist, but we don't know how to do it for the moment. And of course, for future questions, we would like to know what happens if our kernel function is allowed to be singular to cover these fractional Laplacian cases. And the other very interesting, but perhaps very difficult question is high dimension, but without reduced symmetry. I think my time is up. I'll just list some extensions to systems. With you
have 2 minutes, don't worry, Yihong. You can speak 2 minutes more.
All right. I'll just list some preprints or recent appeared papers. These are mostly about systems with a non-local diffusion and a free boundary, in dimension 1. And some appeared, some are being reviewed. I think I'll stop here now. Thank you.
Thank you, Yihong, for this very clear talk and interesting results. Maybe from the first to the audience, please raise the hand if you have a question, and I will give you then permission to speak. Okay, so far no question. I have some question. So I think the asymptotic behavior to study if you have a nonlinearity f of u in your diffusion equation, even in one dimension, but non-local, is quite difficult, I would say. I mean, okay, you have a specific nonlinearity, 2 times 1 minus u, but can you nevertheless say a little bit something how you determined the asymptotic behavior?
Yes.
With a long time asymptotic behavior.
Yeah.
Because it is nevertheless unusual, in particular for this, I think that the zero counting method of Professor Montano is actually failing. That's the reason why I'm saying this.
Yeah.
In particular, when you have a when you have a symmetric kernel with compact support and which is not singular. So
Yeah.
I'm very interested how you, even for FisherKPP,
yes,
nonlinearity are doing this.
To put it simply, basically, the method is you guess it right, and then construct up and lower solutions. The guess for those cases, like let me say, so these ones. So when you have these C0, so you can start your guess with. So you believe your solution would more or less behave like the traveling wave profile, but
Okay.
you have to modify it because it's not accurate. You have to modify it, but how to modify it? You have to, you guess, do lots of try and error kind of thing. Once you guess it right, then you can get it. So it's difficult. But of course, for this accelerated spreading, it's more difficult because you really have no idea how the solution look like. You don't have a wave profile. And then actually, what helped us was that actually for this accelerated spreading, you really don't have to know the profile that well in order to get these kind of estimate. It's not very, very accurate, but it's the order is right, it's accurate.
I see.
So we in this paper actually we first used some kind of profile function to approximate the population density, and that was for a case we didn't discuss spreading rate, but somehow that guess helped us. Yeah. So in these cases you don't have a profile for you, and we are lucky that we found a rather rough guess worked for us.
I see.
Yeah.
Good. That's at least this answers some questions. Are there more questions by the attendees, please? Yeah, Ben, please. Ben, you can speak.
Yes, I don't have a question. I would like to add a comment that there was quite a lot of work done on KPP equation with stochastic term, with the Wiener type noise. And then there were also interesting papers where the movements of the free boundary under the influence of noise was studied, and what is presented in this talk, in fact, opens many new questions in the stochastic case as well, because such a situation as in today's talk has not been studied before.
Oh, thanks, Ben. That's very interesting. I would like to know more. Perhaps, hopefully, we can. Yeah, we can meet maybe in Sydney or in Armadale to talk more. Yeah.
Why not?
Yeah, that's very interesting. Yeah.
Okay, thanks.
Yeah, thank you, Ben.
Thanks.
Are there more questions or comments by the attendees? Okay, then maybe I will close now the session, and you all should have received an email by me. Now there's coming actually, I think there's already a reminder. So in the email you find another password for a coffee break where you can join us and Yihong briefly, and where you can ask also again question in person to Yihong to the talk, but also of course some informal question. And yeah, so please join us, and thank you Yihong again. Please join me in thanking Yihong for this nice and clear talk. And yeah, let's see you next week.
Thanks, Daniel. Thanks everyone for coming.
Bye guys.